We'll go through some examples. Consider this differential equation. There are two parts to the solution. One is the complementary function, the other is particular integral. To find the complementary function that completes the solution, you ignore this part. So this is called the homogeneous equation. Then you try this one. Why should you try this? Because this is the eigenfunction of the derivative. So you try that. So you will end up with these two results. Then you plug in those results in the differential equation, because this is what the trial solution is. This is the differential equation. So once you plug in these guys, k is forced to be non-zero. Why? Because if k is 0, the solution is trivial, useless. Because of that, we force it to be non-zero. So once we do that, you can plug in. You can pull out these guys. You will end up with this. So k is not equal to 0. E to the power lambda x is not equal to 0. So this should be equal to 0. From this you get lambda is equal to plus or minus 3i. So real part is 0, that is alpha. Imaginary part is 3. So you can write the answer as yc is equal to e to the power alpha x, a cos beta x plus b sin beta x. Look, I have listed those in the board. This one. When you get these type of solutions, here you get 0 plus or minus 3i. So beta is 3, alpha is 0. So when you do that, you will end up with this. So e to the power 0 is 1. Multiplication by 1 doesn't make any difference. So this is the solution. This is the complementary function. Now to find the particular integral, you consider the entire equation. This is where you actually find the solution. This part completes the solution. Once you add the complementary solution, you will get the full set of solutions. But if you just take this solution itself, right, it is a solution. Right. But this one itself is not a solution. It is the solution to this one, the homogeneous equation. Once you add something else, it is not a solution. Okay. Now, you have this, you pull out d square plus 9. Now divide. Now you can break this into two parts. Now apply this rule. Look, here you apply the rule in different ways. Here what should you do? Your alpha is minus 1. Substitute minus 1 for d. But here, how should you do? Here b is 1. It's a function of d squared. For d squared, you substitute minus 1 squared. There's a difference. Look. What is this value? This is minus 1. But this is plus 1. The place where you write the square is different. Here it is inside, here it is outside. So this gives you minus 1. So 9 minus 1 is 8. Here 9 plus 1 is 10. So this is the complementary solution. I'm sorry. This is a particular. I made a mistake. Hold on. This is yp. Now you can write the complete primitive or general solution as the sum of these two. This is the complementary, this is the particular, where a and b are arbitrary constants. So it's not that difficult. Now if you move to the next one, this one, again, you don't have to go through this because we have been going through this over and over again in the previous chapter. Therefore, I'll just write the complementary solution. You know how to get it. Then particular integral. You consider the full equation. Write this in terms of d. This is d squared. This is 2dy, like that. Now, you pull out y to the right-hand side. You cannot do this. If you write y here, it will be wrong. Because you cannot pull out y from the operator. I messed up with this, sorry. I think it's in my shirt now. Okay, so you have this. You divide it by this one. Now, how would you do this? Now, if you have trigonometric functions, sine or cosine, you search for functions of d squared. Yes, this is a function of d squared, but look, you have a part like this. But still, you can handle this one. We violate all these algebraic rules. So you substitute minus 2 squared here. That's all. You ignore this one. You get minus 1. So minus 4. 5 minus 4 means 1. So you have this one. Now, still you have the same problem. You cannot substitute anything to d. So you make it a square multiplied by the conjugate. Now you get 4d squared minus 1 in the downstairs. Upstairs you get this. Now again I told you, you can do it in 3 different ways. All 3 different ways give you the same answer. Here you deal with this. You consider the downstairs and again do the same thing. Substitute minus 2 squared here. Now this is minus 16, minus 1, minus 17. Upstairs you have 2d minus 1 times sine 2x. Now, just consider the upstairs, this part. So what is this? 2d times this means what? You differentiate this, you get 2 cos 2x multiplied by 2. Minus 1 times sine 2x is this. So this is the particular integral. Now the general solution is this one. Now you substitute these guys. Where constants. Okay. So this is how you do it. It's not that difficult. Sometimes this may be easier than the method of undetermined coefficients. Why? There you have to solve a lot of simultaneous equations. Here we don't have to. Okay. We'll do one more problem which involves a polynomial. So we didn't have a formula for this. When you have a polynomial in the right hand side, look, in this set of formulas we don't have one for that. We'll see how to deal with that. Recall this series, right? This one you know what it is. I mean, you can even obtain these two from geometric series. However, these series are convergent when mod x is less than 1. Now let's take this differential equation. The complementary, we don't have to bother too much about complementary function. We do it in the same way that we did in the previous case. So this is the complementary function where k1 and k2 are arbitrary constants. Now, particular integral. You consider the entire equation, full equation, replace these guys by d operator, and make y the subject. So you pull out this y to the right hand side and then make y the subject. Don't write y here, it's wrong. Because if you write y, it is like y d over dx. No, it should be dy by dx. So y should be in the right hand side. So then you can play freely with this algebra. Divided by this. Now what should we do? We don't have a formula for this. But you can expand something like this as a series in this fashion. So I'll bring the constant to the front. Because you can easily make this one 1. Make this number 1. So I pull out 4, then I have this one. Because when I pull out 4, this becomes 1. This becomes 4d plus d squared over 4. Now it is like what? 1 plus x, that series. Look. It is exactly like this series. But here, look, mod x should be less than 1. But here we don't have that restriction. The operator theory allows us to do that. We don't care. We simply don't care, right? When we deal with these d operators, we just play with those rules very freely. We don't simply care, right? So we don't care whether the modulus of this is less than 1 or not, because the operator theory allows us to do that, right? Norms of those operators and stuff like that can be used to prove that, but that's beyond our scope, so we don't care what it is. But we can simply write the series like that. Don't write this is mod of this is less than 1. You don't have to. So this 1 minus this guy plus the square of this, cube of this. This side you have 7x plus 3. Now look, 7x plus 3. Now we know that if you differentiate this twice, like d2, d squared, If you put d squared in front, this will be 0. If you differentiate this by ones, like, then you get 7. Okay, remember that. Now let's expand. Now you can bring this 7x plus 3 here close to the operator. So first time 1 times 7x plus 3, then this times this one. But after that, what happens? Every term carries either second derivative or any higher derivative. Look, second derivative d squared or any higher derivative. Therefore, after this you don't care, because when you differentiate 2 times or more, this will be 0. So higher order derivatives will make it 0. So you have this one. Here again you have second derivative. So you don't care. I mean, I divided both by 4. Here this term will be 0, because when you differentiate this twice, it will be 0. Oh, I had to close the bracket. Then this is this. You don't care this term, you simply consider this d times this one. You differentiate this once. When you differentiate, you get 7. So this bracket will be 7x minus 4. So this is the complementary function. I'm sorry, particular integral. It is this. So the complete primitive or the general solution is what? The sum of these three. So I'm sorry, these two. So this complementary function, this particular integral. So that we are k1 and k2 are arbitrary constants. Right. So that's how we deal with d operators when you have a polynomial in the right hand side. Okay. Thanks.